Well, in the last class we talked about how to analyze the solar spectrum, and we observed that basically from the solar spectrum we observed two things. One is the overall broad features which quite resemble a black body, and basically we are getting a black body radiation, right, at temperatures around 5800 degree Kelvin. And the second thing were absorption lines. And in the last class basically we discussed more about the black body radiation and the various effects, and we also talked about photosphere, chromosphere and other stuff as well. Today we would like to talk about the absorption lines. Okay, now you see that there are basically three types of spectrum, right? One is the continuous spectrum here, another is the emission spectrum, and then we have the absorption spectrum. And this is what we observe in the solar case, solar spectrum. Now incidentally it has been observed, as you can see on the screen, different elements have different spectra, right? Both emission and absorption. For example, here I have shown you the emission as well as absorption lines for hydrogen atom. And here along with hydrogen I have shown you the various spectral lines of these elements from hydrogen, helium, lithium, oxygen, and you can see this in the visible range, whatever wavelengths are there. Of course there are in other ranges beyond the visible range, but I am not showing them to you right now. And if you will watch closely, so what we are observing spectral lines. So one is that they are at different energies. No, not different energy. So what does this x-axis mean? This x-axis here is basically showing you different wavelength, but that does correspond to energy. Okay, so basically we are getting information about the energy lines of these various elements at different energies. Okay, by different wavelengths I mean different energies. Now another thing to notice is that some of the spectral lines are quite intense. Say for example this one quite intense compared to the other one. Here you see this one is quite intense compared to the other one. Now why is it so? And we would like to investigate this issue in this lecture. Let us recapitulate about what we have observed till now, what information we have obtained till now from stellar spectra. Okay, so basically what we observed is that from the, again I am repeating sort of, so this was overall, from the overall nature we obtained a black body feature, and then from these very different spikes we observed information about the spectral lines, absorption spectra, which tell us information about the various spectral lines of the elements. Now what I am going to tell you is that these spectral lines, of course we do know that black body, from the black body itself we can get information about the effective temperature. Okay, we discussed it, how to do so using Wien's law, using Stefan-Boltzmann law. Okay, so we can get effective temperature using two black bodies law, Stefan-Boltzmann law and also Wien's law. Now what I am saying here is that not only the black body, the overall curve, but even from these spectral lines, the absorption spectra, we can also get information about the temperature or effective, T effective, effective temperature. Now, so the question arises is that how can absorption line tell us information about spectrum? Okay. Well, you see, inside the star, they are basically hot gases, right? Now, atoms in such a hot gas are moving at very high speed, and they are continually colliding with one another and with any loose electrons. Now, what can happen? As a result, they can be excited, okay? The atoms can be excited or they can be de-excited. Now, when I say excited, I mean to say that the electrons will be moving to higher level, and de-excitation means electrons will be moving to lower level. Fine. Now, you see, this will happen due to the collisions as well as by the absorption and the emission of light. Now, the speed of atoms in this gas, it depends on the temperature. When the temperature is high, so the energy and the speed of the collisions. So what does this mean? This means that hotter the gas, therefore the more likely that electrons will occupy the outermost orbit. And this means that corresponds to the highest energy levels, outermost orbit. So again, let me write it down. Hotter the gas, the more likely that electrons will occupy outermost orbits, which corresponds to highest energy levels, right? Now, this means that the level where the electrons start their upward jump in a gas, it can basically serve as an indicator of how hot basically. So this thing, how an electron is moving. Okay, so let me again emphasize. You see, the more hot a gas is, what will happen? The more likely that electrons will occupy the outermost orbit, which corresponds to the highest energy levels. Now this means that the levels where the electrons start their upward jump in the gas, and suppose this is an atom, they start their upward jump, what will happen? That will serve as an indicator to how hot the gas is. So in a way, the absorption lines, so this is an indicator of temperature. So in a way, the absorption lines in a spectrum, it gives us information about the temperature of the region where the lines originate. So temperature of region where lines originate. Okay. So what next? Well, let us now talk about, so with some preliminary idea as well as detailed analysis, detailed discussion on how to analyze the star spectrum, let us now talk about the various features of stellar spectra. Okay. Now, you see, a typical spectrum of a star, it basically consists of a continuum on which are superimposed dark absorption lines. Note that sometimes even emission lines are also present. You remember I talked about this when I talked about the solar case. So the scenario is like this. Suppose we have got an excitation, and as a result you see a dark absorption line corresponding to this energy, but during de-excitation we can have this path along with these separate paths as well. So what we will observe is that we will observe 1, 2, 3 here for this particular case, 3 more transitions, but these have what? Lower energies. So at lower energy or at larger wavelengths we will be observing sort of emission lines. Okay, now the next feature of stellar spectra is that individual stars differ widely from one another. In brightness and also spectral details. Now what does this mean? Let me show you an example. That will be a better thing to do. See here, I have shown you the spectrum of an A star and also a G star. Now what is A and what is G, I will just talk about it in a moment, but for you just think of it like this. I am showing you 2 different spectrum, each belonging to a different star, and you see the absorption lines. Not only that, 2 things are to be observed. One is the overall black body feature. The peak is somewhere around here, and here the peak is somewhat in a different here. So this means that they have different overall temperatures. Next, look at the absorption lines. The pattern is also very much different. So this means that they differ from each other. These 2 stars here, they differ both in terms of brightness, even effective temperature, and also the spectral features as well. Now remember that this is quite similar to the previous case here that I have just shown you previously as well. On your screen you can see the spectra for different elements. So stars, they also have different spectra, absorption lines, brightness, the various details similar to that of the elements as well. You see each element has its own set of emission and absorption spectra, spectral details. It is because each one has different set of energy levels. Okay, fine. So now let me talk about the third feature. Well, you see, solar spectrum. Let's talk about the solar spectrum. It consists of, we already know, I'm just writing it down, continuous background, okay, superimposed by dark lines, and these are known as Fraunhofer lines. Fine. Now let's talk about the next feature. Well, you see, the intensity of spectral lines, they in fact indicate the abundance of what? Various elements. Now this is new, abundance. What I want to say is that how much of an element is there. So they indicate the abundance of various elements to which the lines belong. Okay? Now, let me talk about the fifth one. Well, what important lines are there? Of course, this is important. Well, most important lines in the stellar spectrum are due to hydrogen, helium, carbon, oxygen. Not only that, but also both neutral and ionized metal atoms as well. Also note that along with them sometimes even bands are also there. Okay, bands in the spectrum, of course, they are also there. Now these are caused by molecules, both vibrational and rotational levels as well. Now, what molecules? Such as, you see, TiO2, zirconium dioxide. These are some of the important cases. Okay, some of the important molecular bands. Now, you see, the next feature is quite interesting. Well, one of the most earliest uses of stellar spectra was to classify stars. So, spectra, it was used basically to classify stars. Now this classification is known as spectral classification. So previously we were talking about 1D grouping, remember, where we in terms of the apparent magnitude. Next one was again 1D grouping, a little bit better. After knowing the information about the distance, we can do absolute magnitude grouping. So we already talked about these two groupings. Now this is a different grouping. So spectral classification. Okay, now, so how was this classification done? Well, you see, as I was saying, one of the earliest uses of stellar spectra was to classify stars, and this also on the basis of strength. You see, in this spectrum, okay, just wait for some time, I will show you the real stuff. Well, in the spectrum, sometimes you see like this, one line is quite dark, thick compared to the other ones. Now they can both correspond, to different elements as well. Now this is a spectrum of a star, say X. Now in the star we are getting two spectra, two lines. Now one is quite thick. Now there can be many reasons of thickness. I will also talk about it. Now the primary reason is more abundance, the thickness of the lines. So if these three correspond to three different elements, then from this very simply you can say that A element is much more in this star compared to B and C. Now this is very preliminary discussion. We will talk more about the details of how to encode this information from the spectral lines. Just wait for a few minutes. So as I was saying, people tried to initially classify stars on the basis of the strength of certain, not all, certain spectral lines only. Okay, so this was the spectral classification. Later on, after the work of Dr. M.N. Shah, as you know, he was an Indian scientist, physicist, it was discovered that basically the relative strength of the spectral lines they depend on the star's temperature. Okay, now I will talk about this part after some time. Okay, we will have a lots of discussion on this as well as detailed calculations as well. But first, let me talk about the different. So, what I want to know is that we have done some sort of analysis of a star spectrum, what is there. Now, the question is, well, we have a very basic question here. So, this is the question I would like to ask. So, how does this information that we have so far discussed till now about the origin of the spectral lines, it helps us? How does it help us in analyzing spectra? Okay, let's see. Well, firstly, so information obtained, how does it help us? Now, let me talk about the first very basic information. Well, firstly, we know that each element provides a unique set of spectral lines. Well, we know that. So, observing a spectrum of a star, what will it do? It will immediately tell us about what elements are present. Now, when I say what elements are present, which elements? The elements inside or the elements outside? Well, of course, remember, we are getting information from the surface, so we can say only about them only. So, from the spectra, we can only get information about the elements that are present in its atmosphere. That is the outer region only. Okay. We can get some information about the inner ones as well, but let me talk about it later on. So we get the first information that we get is the information about abundance of elements. Okay. But remember that the absence of an element spectral line does not necessarily mean that the element itself is absent. Why? Well, we have just seen that the temperature and the pressure in a star's atmosphere will determine what types of atoms are able to produce absorption lines. You see, only if the physical condition in a star's photosphere are such that lines of an element should be there, then we can conclude that the absence of observable spectral lines implies low abundance of the elements. I will talk more about it through an example later on. But right now, let me qualitatively give you some idea. Suppose you say two stars have identical temperature and pressure, but the lines of, say, sodium are stronger in one of the stars compared to the other. Now, as I have said, stronger lines mean that there are more atoms in the stellar photosphere absorbing light. Therefore, we know immediately that the star with stronger sodium lines contain more sodium. Now, in fact, we need to confirm this. We need complex calculations to determine exactly how much more, but these calculations can be done. Remember, these calculations can be done for any element observed in any star with any temperature and pressure. So I have just now talked about a very basic idea, but there are certain catches as well. I'll talk about it in a minute. Secondly, you see, the nature. The first information, we talk about the abundance of elements. Fine. Now, the second information that we get, you see, the nature of the spectrum. Nature of the spectrum, whether emission or absorption, it depends on the temperature. Actually depends, right? It depends on the temperature prevailing in the atmosphere through which the starlight passes. So this means that the nature of the spectrum, this in fact gives us an idea about the star's atmosphere, about the temperature of star's atmosphere. Okay. It is interesting to note that in fact we can also get information about from the spectra about the motion of stars. It is very exciting. You just observe the spectra and in fact you can get idea about the motion of the stars. Well, suppose there is a star and it is not moving with respect to us, then the wavelength corresponding to each element will be the same as we measure here on Earth, right? But suppose the star moves towards or away from us, that means radial velocity. Suppose there is a radial motion in the star. Now, if this is Earth and this is a star, we can have two types of motion. One is transverse motion, where the distance remains the same, or another is motion towards us or away from us. Here, so this is radial motion. This is radial motion and this is transverse motion. Now I am talking about radial motion as well right now. Now what will happen is that if they are moving towards or away from us, then we must consider the Doppler effect, and we will see that all the spectral lines of the stars, they are shifted towards the red end of the spectrum of the star if the star is moving from us, or towards the blue or violet end if it is moving toward us. Let me show you an example. See here. So this is the simple case. Which one? This one. This is the what happens if the star doesn't move with respect to us, stationary case. Suppose there is a shift or there is a motion of the star towards us or away from us, then there will be a shift observed in the Doppler due to the Doppler effect, and we will observe this in the spectrum as you can see here. The greater the shift, in fact, it means that the faster the star is moving. So what we will observe is that the spectral lines of moving stars are shifted towards the red end or red shifted. of the spectrum if they are moving away from us, and it will be moving towards the blue side here, blue shifted. So compared to the stationary case, it is shifted towards the blue side if it is moving towards us. So as I was saying, the greater the shift, the more the difference. It means that the more is speed, the more faster they are moving. Now such type of motion along with the line of sight between the stars, as I was saying, and the observer, is a radial motion. And in fact, you will be astonished to know that we can measure this radial velocity of the stars in terms of kilometer per second, and such measurements have been done. But remember, these wavelength shifts, they are unaffected by transverse or proper motion. Proper motion means transverse motion across our line of sight here. So this is proper motion and this is radial motion. So the shifting of wavelength here and here, this is red shifted, this is blue shifted, as I have just shown you now. You will observe this in the case of radial motion only. Fine. Now you see, we can in fact use the Doppler effect. So we just use the Doppler effect to measure whether a star is moving towards us or away from us. But along with that, we can also use the Doppler effect to measure how fast a star rotates. So we can get also information about rotation of star from the spectral lines. Well, you see, let me show you through a picture here, as you can see on the screen. Now there are two stars. You see, we are seeing a top view each of them. Now suppose this star is rotating. Now what will happen is that because of the rotation, one of its side is approaching us, this side, and here we are. This is Earth and this is the star. Suppose because of the rotation, one of the side is approaching us while the other side is receding. Note that this will be the case unless the axis of rotation happens to be pointed exactly towards us. Okay. Now let us analyze the entire light from this star at once. Now, due to the Doppler shift here, you see, due to the Doppler effect, what will happen is that the lines in the light that come from the side of the star rotating towards us, this one, are shifted to shorter wavelength, and the lines in the light from the opposite edge of the star are shifted to longer wavelength. So what will happen is that each observed spectral line is thus a sum of spectral lines originating from different speeds with respect to us. There will be a speed distribution. So each point, now you see, each point on the star has its own Doppler shift. And so what will happen as a result is that the Doppler line that we will see from the whole star is actually much wider because of this spreading towards shorter and longer wavelength than it would be if the star here, so there is a spreading compared to the case if the star were not rotating. Now this effect is known as line broadening, and in fact the amount of broadening, it can tell us the speed at which the stars rotate. Okay, so now let me talk about the fifth information that we can get. And well, let me talk about size of the star. Fine. Well, we have already discussed some of the things related to how to do a measurement. Let me clarify. Well, as you can see, we can get an idea about the size of the star using the Stefan Boltzmann law. or basically the Bragg body approximation. Now from this law we have this flux proportional to T to the power 4, right? So let me write down the luminosity of the star, so which is surface area into radiant flux. So it is this expression, L is equal to 4 pi r square sigma T to the power 4. Now if we compare two stars, star 1 and star 2, then we have this expression. But we do know what is such an expression from our discussion on magnitudes previously. Now if we compare these two cases, then you see we have got a relationship between radius, temperature and magnitude. So what we can do using this relation, we can compare the radii of two stars. Let me give you an example here. You see, suppose the surface temperature of star A and B are found to be equal, and the absolute magnitude of B is larger than A by 10. Then what will happen is that we already have this relationship, m1 minus m2 is minus 10, and so we have R2. Using this relationship we will obtain that R2 is equal to 0.01 into R1. So this means that the radius of star A is 100 times that of star B. Now we will talk about more consequences. What can you say about the star as a result of this temperature and radius when I talk about the HR diagram? But first let me give you yet another example here. So suppose two stars of the same mass emit different. What I want to emphasize here is a very interesting fact here. So the fact is, two stars of the same mass, they in fact emit different types of radiation even at the same temperature. Now how is it so? Well, we have just derived, you see, this relationship here. Now let me use this for two stars A and B. So luminosity versus radius and temperature. So let me consider this case here. Suppose one star having twice the radius of sun, another star is basically the sun in fact. However, the first star has the same temperature as the sun. Now since each centimeter square of each surface emits the same amount of radiation, so this means that the larger star here emits more radiation because it has a large surface area. In fact, it emits 4 times as much radiation, which we can obtain using this relationship here. Okay, so using this relationship we can get idea about the different luminosity, and since they are different luminosity, so this means that even if they have the same mass, right? So two stars, same mass, so one is the sun, another is just like the sun but not the sun, which although has the same mass as the sun as well as temperature, but its radius is twice as large that of the sun. So this is what we were comparing, and the result we obtained as a result of this double of radius, we observe that its luminosity is in fact 4 times is that of our sun. Now talk about another fact. So just now I wish to talk to you about how to get an idea about the size of the star. Now the first way is to use the Stefan Boltzmann law, and we observed through 2 examples how we can get idea about the size of the star. Okay, through this. In fact, now let me talk about the effect of pressure. Again, this is a part of the determination of size, whether at least we can tell about whether the star has bigger size or not using the spectral features. Now let me talk about the effect of pressure on photosphere. You see, suppose we want to determine whether a star is a giant or not. Okay, so we will be discussing the effect of pressure on photosphere. So as I was saying, suppose we want to determine whether a star is a giant or a normal star. Now, a giant star has a very large extended photosphere, large photosphere. Now, because it is so large, a giant star's atoms are spread over a very large volume. So what does this mean? This means that the density of particles in the star's photosphere, low density. So, density is low. As a result, the pressure in the giant photosphere is also low. And this affects the spectrum in two ways. Okay, now first, you see what happens is that a star with a low pressure photosphere. So, a star with low pressure photosphere, what will happen in it? It will show, in fact, narrower spectral lines. Spectral lines. Why? Now, before why, let me say this. So, a star with low pressure photosphere will show narrower lines compared to a star of the same temperature with a higher pressure photosphere. Now, this reason is due to the collisions between particles in the star's photosphere. You see, more collisions lead to broader spectral lines. Also, the collisions will be more frequent in a high density environment. Okay, so this is one of the reasons. Secondly, you see, more atoms are ionized in a giant star than a star like the Sun with the same temperature. The ionization of atoms in a star's outer layers is caused mainly by photons. Fine. And the amount of energy carried by photons is determined by temperature. But how long, remember, how long do the atoms stay ionized? This actually depends in part on the pressure of the photosphere. So compared to what happens in the Sun, which has a relatively dense photosphere, ionized atoms in a giant star's photosphere are less likely to pass closely enough to electrons to interact. Why? Because they have low density, large volume. And so, because of this low density, what happens, you see, ionized atoms in a giant star's photosphere are less likely to pass close to each other and also close enough to electrons to interact and combine with one or more of them, thereby becoming neutral again. It is important to note that ionized atoms have different spectra from atoms that are neutral. Okay, so we have talked about the various types of information obtained from a star, okay, which can help us in analyzing stellar spectra. And we have also discussed about the various features of stellar spectra. Okay.